Today I'll talk about mathematical basis of convoluted neural network. This is one of my series of lecture on machine learning. Image analysis can be done using a usual deep neural network. For that we can feed a image with dimensions h and w to the input layer with n is equal to h multiplied by w number of neurons. If there are m neurons in the first hidden layer after the input layer, then total weights that needs to be learned are h multiplied by w multiplied by m. These are the number of weights, and the biases would be the m, that is the number of neurons in the first hidden layer. So the number of parameters to teach is huge. Moreover, the usual deep neural network does not take into account spatial relationship between pixels, as it treats pixels far apart on same footing. So what are the features of convoluted neural network? There is a concept of local receptive field. By this I mean that the adjacent pixels which are spatially related are fed to a single neuron with the weights, and these weights are shared. So there are shared weights and biases in convolutional layer. So this is the neuron in convolutional layer. Then there is a concept of pooling in CNN. By pooling, I mean that the adjacent pixels are pooled to reduce the trainable parameters. And the fourth feature of CNN is that CNN are well adapted to translation invariance of images. By translation invariance, I mean that if the image is shifted, even then CNN can identify the object. The images in this lecture I have taken from various internet resources, and I have written the link for those internet resources below my each slide. So let us see what is a convoluted neural network. So we use filters, and these filters, they are shifted on the images, and the sum of dot product is noted down. So if this filter is shifted in this image, one pixel at a time, then this image is converted into the output with reduced number of dimensions and information related to adjacent pixels. And the filter values are nothing but the weights, and these weights are trained in the training process of convoluted neural networks. So these numbers we get by training the network, and these are nothing but the shared weights. So this is the concept of shared weights. So this is the filter with these weights, and these are shared because this filter is moved on this image usually one pixel at a time, and these weights are learned to get the output with reduced dimensions so that we have less number of parameters to be trained. In order to get the representation of pixels on the edge, we can pad our image, and this hyperparameter p, if it is set to 1, then we have a padding of single pixels around the image. And it may be p is equal to 2 for 2 pixels around our image. Then there is a concept of stride length. When this filter is moved over the image 1 pixel at a time, it means that stride length S is equal to 1. So this filter is moved by 1 pixel at a time. However, if this filter is moved 2 pixels at a time, then we say that stride length S is equal to 2, and we get a much output with much reduced dimensions. So this is the complete convoluted neural network. We have an input image. We do the convolution. This is the convolutional layer. Then we may do pooling. Then there is a fully connected deep neural network to get the final output. So this part is known as feature extraction, and this part is known as neural network. In fact, this entire thing is known as convoluted neural network. So what is the mathematical basis of convoluted neural network? This is the forward propagation. There is an input image X. Then we do the convolution, which is denoted by X asterisk F. And this F is nothing but filter. And we need to learn the values of these filter weights or shared weights. Then there is an activation function, usually a sigmoid function. We may use some other function. Then there is this part of the fully connected neural network where there is linear transformation. As in usual neural network, this is linear transformation followed by the activation function, which may be sigmoid. Then there is output. So this part of lecture of the usual type of neural network I have covered in my previous video. The link is shown above. So this is the forward propagation. Then this is backward propagation, and for backward propagation we calculate the derivatives, because in order to adjust the filter weights we need to find the derivative of the cost function, which is nothing but error E with respect to F. So for getting this derivation of error with respect to filter, we will use the chain rule. So we go from this layer to convolution layer by using the chain rule. This I have taken from this very useful resource. So first of all, let us, because there are parameters in two layer. One is the linear transformation layer parameter W, which is matrix here, and parameter F or the shared weights, which is again a matrix. So to adjust the weights of this layer, we need to do back propagation, and we use the derivatives with the help of chain rule. We get the derivative of error with respect to the derivative of this matrix W. So this is the derivative final we need. And when we get this derivative, we can get the new weights is equal to old weight minus learning rate multiplied by the derivative of error with respect to W. So this is the how we learn these weights are learned. These are weights in the linear transformation part of the deep neural network. And to get the shared weights or to adjust the shared weights, to learn the shared weights, we can again make use of the chain rule of these derivatives. So we get the derivative of error with respect to the shared weights, and this is how the shared weights are adjusted. So this is the mathematics behind the convoluted neural network. I hope this video is useful for you. Thank you very much.